have. Do you know what x is at the instant in time? Yes. That's Tom's distance, right? Wasn't it like 56,000, something like that? Okay, we know what that is. Do you know what y is at the instant in time? Yes. Do you know dx dt, how fast Tom's moving? Yes. And then do you know dy dt? Yes. Do you know what h is at the moment in time? No, not directly. How about dh dt? That's what we're trying to find out, so I'm happy to see that. So there's only one thing I don't know, and that's h. So now what I'm going to do, yes? Yeah, I have actually an equation right here to solve for h. It comes off this triangle. But see, now I can fix everything in time. What was x again? 57,600. And then y was 36,000, right? So I should be able to plug this x and this y. See, I can fix everything now because I've done the derivative already. So I can take the x here, plug it in, the y. I can plug in dx, dy in here. To get h, I'm going to just use that equation right there, or this one. Doesn't matter which one I use. So let's go get h. I'm going to use this equation. This is 144 plus, okay, x was 57,600 plus y, which is 36,000. All of that squared equals h squared. And now I need my calculator for that. It's what? It's a lot. Did you take the square root yet? Take the square root. Yeah, it's still a big number. So let me do it. Let's see, 144 plus parentheses. Yeah, big number. Take the square root. All right, so once I do that, I take the square root on both sides to get h, right? And I get 93,600, yes? Nice. So I know what h is. Once I have that, it's all plug and chug now. I'm just going to plug everything in and chug out an answer. It's going to be ugly, but hey, in the real world, numbers never are nice, okay? So all right, I'm about to do this. All right, I have 2 times, okay, x plus y was 57,600 plus 36,000. Okay, that times, what was dx dt? It's not 8 feet per second. Remember we switched it? What was it? 28,000. What was it? 800, sorry. 28,800. That's dx dt plus dy dt, which was 36,000, right? Equals 2 times h, which we just found was 93,600, and then times dh dt. Do y'all see what I'm doing here? 2 times x plus y, that's his speed, that's her speed in feet per hour. Everything has to be in hours or seconds, but I decided to go to hours, so, and then 2 times that. So I'm going to figure out all the left side first.
Wait, I have a question.
Yes?
For 93,000, that number.
600, yeah?
You just added 57,600 plus 36,000, and that's.
Squared them.
Oh.
And then added 144, and then took the square root.
And that's what it equals to?
Yes.
Okay.
I think someone else got that as well. Yeah, that's right. Oh yeah, you could have canceled these 2's out. Let me just figure out what we get here. I'm just going to do the left side first. It's huge, yeah.
It's like extremely close to 3,600.
It should be, yeah. Okay, so when I multiply the left side, oh my gosh. You know what I'm doing? I'm going to take that number on my calculator, and then I'm going to divide by 2, and then divide by 93,600. and I get I got 64,800. Anyone else get that?
I got that as well.
You got that? 64,800. So taking this and dividing it by 2 times 93,600, right, gets rid of it over here. You should get, say it again, what was it? 64,800 is my DHDT, and that's measured in what? So H is the distance, and that's measured in feet, and then time was measured in hours. Now we could get that back to feet per second, couldn't we? You could just someone divide that by 3,600. What happens if you divide that by 3,600? You get 18, which is really what? Think about it. If you divide this by 3,600, you get back to feet per second. What's her speed? Her speed is 10, and his is 8. And if you look at them, that's what, 18, isn't it? But here's the deal. They're so far apart from one another that it's almost like they're in a straight line, because there's only 12 feet between them, right? 12 feet, and they're going like this. So the further away you go, the more this is almost like a vertical line. So it's almost like they were back to back, walking away from each other, which should be about 18 feet per second. So the reason we're getting 18 is because there was some rounding issues on our calculator. But either way, the more important part of this problem, the most important thing I wanted you to see, wasn't all the crazy numbers. It was that picture that I drew here, that, and being able to call this X and Y and H, and then seeing that right triangle in there. That's the big part of that problem that you should take away from it, all right? All right, let's try something else. I'm gonna do one of the problems in my notes because it's a good problem to see. How are we doing on time? We still have another hour? What the hell? I'm giving you all this problem. I normally don't give this one first. I give another one, but I get this feeling that y'all can handle this. Read the problem first, and I'll leave the problem up here so you don't have to write it all down, but you can if you want. Oops. There we go. And we are neglecting the curvature of the Earth here. We're going to assume that the Earth is like flat. Well, it is flat, right? No, we're neglecting the curvature of the Earth, right? We're just going to assume, like for the problem's sake, we got flat ground, plane flying horizontally. Pardon me?
Whatever says that 6 miles from the radar station, is that including the height?
Yeah, so this is one of the ambiguities of a problem like this, the interpretation here, is this part where I say that at the moment the plane is 6 miles from the radar station, I mean the distance, if you were to measure from the plane down to the radar station, straight line distance, not vertical distance. I'm not sure if that's what you're asking, but
That's even like horizontal distance.
no, point to point. So I think we should draw a picture. Has everyone had time to read the problem? Okay, so I'm going to have the ground. Here's my I don't know, general picture. Let me start. I'm going to put G. Here's my instant picture. All right, my general picture, I've got the ground. And what's on the ground? The radar station, okay? So it's a point on the ground, right? Or if you want, you can draw a radar station if you like. If you feel like you can keep up with that artistic ability. I know, it's impressive. Here's my radar. But it's really a point on the ground, right? That's what we're going to just look at as a point. And then we have a plane that's flying overhead horizontally. Again, if your artistic skills are not up to my level, don't feel bad, all right? Ooh, needs a wing on the other side. There we go. Obviously, that's an F-16. All right. Plane's flying horizontally. Could I have brought the plane coming in from the right going over this way? Absolutely. Okay, this is totally up to me. All right, the plane is flying overhead. What can we say about the plane? The altitude of the plane is 2 miles. Is that ever going to change? No, that should be fixed. The altitude is 2 miles. So the distance from here to here should be 2m, 2 miles, or 2mi, however you want to do it. That should be fixed both in the general picture and in the instant. That should be the same. All right, I know how fast the plane's going, right? 600 miles per hour. That is a rate of change. That is a derivative, right? It's a derivative of something, though, but I haven't labeled anything on my picture yet. So I'll get to the 600 in a second. Plane's flying directly overhead. At the moment the plane is 6 miles from the radar station, how fast is the angle of the tracking radar changing? What the? Okay, so I need to put something in here. I've got to get an angle in there, right? So imagine this radar is tracking the plane, and the plane is really a point, right? There's like a line connecting those two, right? And that forms this natural angle with the ground, like that, theta. I'll call it theta. So as the plane flies over, theta changes, doesn't it? And I would like to know, at the moment that the plane is 6 miles from the radar station, how fast that angle is changing. The rate of change of the angle. Okay. Let me put some other stuff here. I'm given what I want. Hey, what do I want? D theta dt. I want to know how fast the angle is changing, right? I don't want to know what the angle is. I want to know how fast the angle is changing. And when do I want that? At what moment do I want that? At the point in time that the plane is 6 miles from here to here, right? 6 miles. So let's go to my instant picture, because that's a different picture. So this time I'm just going to put R down here for radar, here P for plane. So not as elaborate of a picture. But this from here to here is 6 miles, right? And I can also label on this picture the distance from here to here is 2 miles, right? That's the instant in time. And then, of course, we've got theta in here, whatever theta is. What am I given? There's something, I need an equation to put things together. I need to be given something with the variable that I can connect to the theta. It's the speed of the plane, but what is that in the picture? I'm looking at this picture here. Speed of the plane is the speed at which this point is moving, right? Speed at which that point is moving. So this is a critical step in the problem. What I'm going to do is I'm going to label, bless you, I'm going to label this side from here to here. I'm going to call that X. Or P, I could have done P for plane. And imagine projecting straight down from that plane down to the ground. Do you agree that as the plane moves, this point moves? Yes? And if this moves, X is doing what? It's shrinking, right? It's getting smaller, but it's moving, right? Do we know how fast that point's moving this way? Same speed as the plane, right? So do you all see that X is changing at a rate of 600 miles per hour? Yes? Do y'all see why I put the X down here? Do y'all see a right triangle in here? Okay. So here, let me write what I'm given. I'm given that the rate at which x changes with respect to time is negative 600. What? Why did I say negative? It's critical. It's shrinking, right? Look at your picture. X is shrinking, right? X is getting smaller. It's not getting bigger. If x were getting bigger, then I would put positive 600. Is this everything I need? Oh, at what moment? At what moment here? At what moment do we want this? At something is 6 miles. Do we have anything labeled over here? Like here it's 6, right? But what am I calling it over here? Because this is, everything's changing over here. We should probably call it h, right? H. So at the moment that h is 6 miles. I have what I want. I have when I want it. I have what I'm given. I have an instant in time picture. I have a general picture. And all I'm missing now is an equation connecting everything, everything together. Connecting what together? This is important. Well, it's all important. What variables am I going to try and connect together? I need theta and x. That's it. Those are the only two variables you have to connect. The fact that h is here doesn't mean that h needs to be in my equation, because here and here, in fact, I don't want h in my equation, because if h was in my equation, then wouldn't dh dt come out? Think about that. If h is in my equation, when I take the derivative, wouldn't I get a dh dt? And do I have any information about dh dt? No. So I actually don't want h in there. I just want an x and a theta. So go to your general picture, look at this, and tell me if there's anything you can think of from your mathematical life that would connect theta and x together. Tangent. Trig function, right? Look, you've got a right triangle, you've got theta, you have the opposite side and adjacent side. The opposite side is 2, right? Always 2. The adjacent side is x. And I'm avoiding, we are avoiding the h. We're trying to stay away from it. Yes, of course you could say sine. Well, no, sine wouldn't connect it. Sine is what, opposite and hypotenuse? We could do cosine adjacent and hypotenuse. But the problem with that is you would have an h in the equation. You don't want h. So tangent is the best way to go. Tangent theta, here's my equation. Tangent of theta equals, what, 2 over x, right? That's an equation based on my picture. That is true. For that picture, this is a true equation. And it connects x and theta together. Yeah? And now what? Derivative, right? I can do a derivative right now. How are you going to take the derivative of this, though? 2 over x. How do you do that? You could do quotient rule, or you could bring the x up as an x to the negative 1 and do your power rule, right? What would you all prefer to do? Quotient or bring the x up? Power. Bring it up and do power? I have a better idea for me. I'm just going to multiply both sides by x. Can I do that? If I multiply this side by x and that side by x, I get this. X tan theta equals 2. And then the left side is just going to be a quick product rule, and then the right side is just derivative is going to be 0. You don't have to do this step, but I'm doing it because I'm avoiding having to mess with this negative exponent stuff. There it is, implicit now. All right, for implicit, we're differentiating with respect to what? Time. The right side's 0. Right? Derivative of the right, derivative of 2 is 0. Derivative of the left is going to require product, right? So it'll be the derivative of the first one times the second plus the derivative of the second one times the first one. And I'm going to scroll this stuff out of here so that I can, well, no, I'll just switch. Get some room up there. All right, here comes my derivative. All right, what is the derivative of x with respect to t? dx dt, all right? That's the derivative of the first one times the second one, tan theta. All right, careful, very careful on the next one. What is the derivative of tangent theta? Secant squared theta. Are you done? What's the derivative of tangent of something? Secant squared of that something. Now chain rule. Derivative of theta. Don't forget, you have to take derivative of theta, the thing that's inside the tangent. And what's the derivative of theta with respect to t? D theta dt. D theta dt, right? D theta dt. Look, in case, I know that some people have trouble with this part. So let me put it this way. If I asked you today on your quiz when you walked in here to take the derivative of this, take derivative, you would say, okay, secant squared, right, of the x squared plus 1, chain rule, times, now the derivative of what's inside, you'd say 2x, right? Okay, that's the same thing we're doing here. What's derivative of tangent of something? Well, secant squared of that something, but then you have to take derivative of what's inside. And what's the derivative of what's inside with respect to t? It's not 1, it's d theta dt. That's your implicit chain rule there. But I'm still not done because I'm in the middle of a product rule, aren't I? So I still have to multiply by x. And then all of that is equal to the right side, which was 0. Are y'all seeing why people don't like these? Students usually don't like these? Are y'all kind of, I mean, it is what it is. Now I'm just going to check to see if I have everything I need. Do I know dx dt?
Yes.
Yes. So I'm happy about that. Do I know what tangent of theta is? No, but look at this triangle. At the instant in time, I have two sides of a right triangle, don't I? Can I solve for this third side? If I solve for this third side, would you be able to tell me what tangent is? Yeah, it'd be this side over this side, wouldn't it? So I should be able to get that. Right now I don't know it, but I should be able to get it. How about secant of theta? And then we'll have to square the answer. But can you get secant? Well, again, if I had all the sides of the triangle, I could get secant, right? So I'm going to need that side. So that I don't know, but I should be able to get it. D theta dt is what I'm looking for. Happy to see that. Do I know what x is at the moment in time? I don't, but I could find it out. Wait a minute, hold on. Isn't x this bottom piece right here? Yeah, so that seems to be like the missing link here. If we could just figure out what x is, we could figure out all this stuff, couldn't we? Pythagorean, right? So let's get x. So we know x squared plus 2 squared is 6 squared. So x squared is, what's that? That's 36. That's 4. Take 4 over, subtract it. 32, which means x is root 32. I've got everything. I hope. Let's see. Y'all can help me write this out. All right. Starting with dx dt. Dx dt was negative 600. All right, times tangent of theta. According to this, tangent is opposite over adjacent, so 2 over root 32, right? And then plus, what is secant? I mean, I know most of you know the whole SOHCAHTOA thing, but secant is the reciprocal of which trig function? Cosine. What's cosine? SOHCAHTOA? Adjacent over hypotenuse. I mean, however you know it. So if cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent, right? So it should be 6 over root 32. But we're squaring it, right? Because it's the secant function, secant of theta, but squared. And then times d theta dt, which is what we're trying to solve for. And then times x, but didn't we just say x was root 32? And then equals 0. So that's everything plugged in. Everyone see where everything came from there? I don't know. I'm kind of a fan of getting a decimal at this point. I would probably bring this to this side first. Right, all of this, because it's negative. Just bring it to the other side, make it positive. And then, yeah, I mean, it's probably good to just do a decimal at this point. So I'm going to get on my calculator right now, and I'm going to do all of this. I'm going to do this, and that'll be some number that'll be sitting in front of d theta dt. So I'm getting 6.36, somewhere around there. 6.36 is what I'm getting for this together with this. And then equals on the other side, remember I'm bringing that over, so I get 212, positive 212 over here, 1,3. I'm getting about d theta dt is approximately 33.3. Anyone else getting that? 33.3? Yes? $33.3 what? So it's our angle, right? Theta, and we're going to measure in radians. Why not degrees? This is a weird thing in math. Why is it not degrees? Why is it radians? It's always radians, okay? It's always radians unless you want to convert to degrees. Everything we always do when we're doing arithmetic involving triangles, everything is in radians unless we want to somehow convert it to degrees, all right? So our answer here is going to be in radians, rads per second, right? And now, can we convert from radians to degrees? How do you do that? Multiply by 180, divide by pi, right? So if you wanted to know what this was in degrees per second, I would take 33.3, multiply by 180, divide by pi. Did I do that right? Yeah, 1,900. Is that right? Oh, this is not seconds. Hold on. Pardon. This is, sorry, my mistake. This is hours because the plane was moving in miles per hour, right? So converting this over, I get 1,907.95 degrees per hour. That makes more sense. 1,900 degrees, that's a lot of degrees, well, kind of, but per hour. So it's not moving very fast at that instant. Why do you think it would be important for a radar station to be able to know how fast it's turning when a plane's flying overhead? Where do you think that would become important? Yeah, if you're trying to shoot it down, right? Like if you're trying to shoot it down, you need to know how fast your turret needs to turn to keep up with that, right? I mean, the fact that human beings don't get along, right, motivates a lot of progress in technology. Would you agree? Right? I mean, the fact that we just don't like each other, and I have my God, you have your God, you know what? I'm going to kill you then. I mean, like that sort of mentality that we've had as a species has really pushed science and technology, hasn't it? No? Am I alone up here? No? I mean, just think about nuclear weapons, right? All right, I can tell that y'all are loving this. The issue with these, I think, is that every problem is different, right? Nothing is the same. Everything is something uniquely its own. But that's the way the real world works, right? If you're an engineer and you're working on a project, right, building a bridge or building an airplane, whatever it is, you know, every project is different, right? Everything is unique. You can't just carbon copy everything. Everything has to be tailor-made to that specific situation. Let's try and do one more, or maybe more than one. Y'all want to do another one? I mean, I know you're tired and you'd like to call it, but look, the more of this you see, the better for you, I think. Would you like me to let you try one? Okay, let me let you try one. Oh, okay. Trying to think of how bad. Yeah, I mean, okay. You want it, you got it. It's not that it's any harder, but the geometry in here that's required is something we haven't talked about. So we'll see if you know the geometry that you need for this problem. A street light is mounted on a pole that's 20 feet high. A 6-foot man walks away from the pole at 7 feet per second. That's a very brisk walk, right? It's a run, basically. Trotting. He's trotting, yes. How fast is his shadow moving along the ground relative to the pole? When I say his shadow, I mean like the tip of his shadow. So should we just, I'm not going to draw anything, but can we at least talk about what's going on? You've got a pole, 20 foot, there's a light on it. You got this guy, 6 foot tall, he's standing here. There's the pole. The light's shining, his shadow should be cast on the ground in front of him, right? Like this. And he is moving, trotting away from the pole at 7 feet per second. And as he does that, what happens to his shadow? Does it get shorter, longer? You'll figure that out for sure. And so the question is, how fast is the tip of his shadow moving away from that pole? So what's the speed of the tip of his shadow? All right, why don't you try, I'm going to give you, let's see how far you can get in 15 minutes. Sound good? Help each other out. If you'd like, you're welcome to use the boards. If anyone wants to draw pictures on the boards and use those, feel free.